Okay, so we are about halfway through chapter 8, and we want to introduce 8.3. So chapter 8 was all about and is all about hypothesis testing. And we spent quite a chunk of time looking at 8.1 and introducing the basics of hypothesis testing. And then we also looked at testing a claim specifically about a population proportion using a hypothesis test in 8.2. And then what we're going to do today is move on to look at testing a claim about a mean of a population. So key concept, testing a claim about a population mean is one of the most important methods presented in this book. That's a fair statement. It's very, very important because this is one of the most common ways statistics is used and that you will see it used in society. So part one of this section deals with the very realistic and commonly used case in which the population standard deviation sigma is not known. Part two includes a brief discussion of the procedure used when S is known, which is very rare. And I think they're supposed to have a sigma there, not an S. They wrote an S on the slide here, like just the standard deviation of the sample, but anytime you have a sample, you can see the standard deviation. So again, the slide needs to be edited. So just drawing on here, that here should be a sigma symbol, just like the symbol right here. So we talked about this a little bit already in chapter 7. We talked about creating a confidence interval, and we talked about the difference between using a normal distribution and using a student t distribution. And that's the key. When sigma is not known, we use the t distribution. And when sigma is known, we use the z distribution. So that's the key difference between the two here, which they will, of course, illustrate through their examples. But just as you are looking at a problem, when you're trying to perform a hypothesis test for the mean of a population, you're going to want to choose the correct distribution. And so you would choose a z distribution or a normal distribution if for some reason you had the rare case where sigma of the population is known. But most of the time, the standard deviation is not known, sigma is not known, and then we use a t distribution. So that's just a decision to think about as we go into these problems. So testing claims about a population mean with sigma not known. So that tells us t distribution. And so the objective, what is the objective? Use a formal hypothesis test to test a claim about a population mean. So just to go through our figures, which we were using when we were doing proportion testing before. So idea is you've got some sort of a claim. So let's say something like, I believe the mean height of students at DVC is less than 6 feet tall. So I would do something like the mean is less than 6 feet. And though we then can take that claim and translate that into a null and alternative hypothesis. And so I would say, all right, the null hypothesis is that the mean value is equal to the specified value. And then my alternative hypothesis, if I'm claiming that the mu value is less than 6 feet, then that would be my alternative hypothesis, as an example. And then from that, we would take the information from a sample and use StatCrunch and the information from a sample, either a summary or maybe they actually give us the data values of some sample. And we would put that into StatCrunch to produce a p-value. And then we would be given some alpha value, typically 5%, but it could be 1% or 10%. And then we would get p using technology, which I'll just refer to for StatCrunch, because in this examples, they won't know which technology they're using, but for us, it's typically StatCrunch. And then if p is less than alpha, then we reject the null. So I'm just trying to put up these reminders of this overview and reminder of the idea of a hypothesis test and what it looks like. And we went through all of these steps for proportion in 8.2, talked about the basics of this whole process in 8.1. And now in 8.3, we're modifying to apply this to a mean of a population. And the difference is we have to determine which distribution to use based on whether sigma is not known or not. But other than that, the process will basically be the same as it was in earlier sections. All right, so let's see how they address this idea of achieving this objective. So they remind us of notation, and what's different in our notation this time. Sample size becomes very important when you're doing a t-distribution, because remember, we have this thing called degrees of freedom, which is equal to 1 less than the sample size. With the t-distribution changes based on the sample size. The larger the sample size, the better. The bigger your sample size, the more the t-distribution just looks like a normal standard distribution. But even with smaller sample sizes, we can still use a t-distribution, assuming that we know that the sample is drawn from a normally distributed population. We'll see these criteria laid out in the coming slides. So sample size does become more important when we're doing a t-distribution. And then instead of doing p for proportion of the population or p hat for the sample, we're doing x bar, which we're used to doing from before for the sample mean. And that means we have the population, the mean of the sample basically ends up being the population mean. The mean of the sample means is the population mean, as we learned back from the central limit theorem. All right, so going through some of these paces here, we have some requirements, and I do believe somewhere along the way you'll have some problems that test to see if you understand these requirements. So let's make sure we understand them or ask questions if we don't. So the requirements are 2. First one is the sample is a simple random sample. You always need to have a simple random sample. The data needs to be collected in a way that's randomized. Biased data will always lead to biased results. And then you have to, for part 2, satisfy one or both of the conditions, namely that the population of the value that you're sampling is normally distributed. So if it were heights, the parameter basically is normally distributed in the population. So if it was heights of students at DVC, I would need to know or believe that the heights in general of students at DVC are normally distributed. Or you can get around that if you're not sure about that or don't believe that to be the case by just having a large enough sample size. So the other satisfactory condition is that n is greater than 30. So it says either or both of these conditions are satisfied. That's a requirement. So you need to either, if you have a sample size that's less than 30 or less, then you need to have some reason to believe that the sample comes from a normally distributed population. So let's remind ourselves that we can check by, meaning we can check to see whether we believe the sample was drawn from a normal population, we can check this by creating a QQ plot or a normal quantile plot. And using the criteria that we looked at before on determining whether a population's values are normally distributed by looking at the QQ plot of a sample. And if it seems to line up in a somewhat straight line without some systematic deviation, then that gives us an argument that the population's values are normally distributed. So if you had a smaller sample size of maybe 25 or 20, then you would want to perhaps make a QQ plot of that sample values to see if it's justified to believe that the population is normally distributed. Because if you don't have more than 30 people, then you're relying on that, the population being normally distributed, for the techniques that we're going to go through for a hypothesis test to work. Okay. All right, so then they're giving us the formula for calculating a test statistic for a t distribution. Again, you can use the formula for a particular value, but in general, we will just rely on StatCrunch to do that for us. And usually we want to look for the p-value. And so they look at the p-values and it says use technology. Which is what we will do. And it says, or you can do table A3 with the degrees of freedom, but we'll just try to use technology. And then the other possibility is to use critical values. And we've discussed that a little bit using the t distribution with the table. But again, even then, it's easier to use technology. So now they're going to look more closely about those requirements that we were just discussing. The requirement of normality or the sample size being greater than 30, if the original population is not itself normally distributed, we use the condition that n is greater than 30 for justifying use of the normal distribution for the sample values from that population. Sample sizes of 15 to 30 are sufficient if the population has a distribution that is not far from normal. So if you do have 30 or less, then 15 to 30 is okay if the population is pretty close to normal. In this text, it says we use the simplified criteria of n being greater than 30 as justification for treating the distribution of sample means as a normal distribution, regardless of how far the distribution departs from a normal distribution. So it's a little bit of a simplification. So they're just discussing these criteria, but we do want to be clear that at least one of those two conditions need to be met. You need to either have a sample size over 30 or have some justification that the population the sample is drawn from is normally distributed or not far from it. All right, so here's some important properties of the t distribution. The t distribution is different for different sample sizes. That's why we have this degrees of freedom, because the bigger the sample size, it changes the distribution and the reliability and what kind of data values allow you to make predictions about the population. The student t distribution has the same general bell shape as the normal distribution. Its wider shape reflects greater variability that is expected when S is used to estimate sigma. Because we're using the t distribution, because we don't know sigma, we're using S, the standard deviation of the sample, to estimate that. And for that reason, we modify the normal distribution into a t distribution to allow for greater variability. The student t distribution has a mean of t equals 0. These were discussed back when we first introduced this t distribution. Standard deviation of the t distribution varies with the sample size and is greater than 1. As the sample size n gets larger, the student t distribution gets closer to the standard normal distribution, which is what I mentioned earlier. All right, so a lot of these properties will sort of not make a lot of sense to folks. It is something to try to think about, but finally they are getting to an example on slide 10 where they're going to actually try to show this in use, show an application. We have 8 slides to consider this example, which is looking at adult sleep. The author obtained times of sleep for randomly selected adults. included in the National Health and Nutrition Example Study, and those times are listed below. So these are the times in hours for the sleeping adults in their study. And they have, here are the unrounded statistics for the sample where N was 12. So they have 12 values here. And they went ahead and showing you the mean and standard deviation value for these values for the data given here. Common recommendation is that adults should sleep between 7 and 9 hours each night. Wouldn't that be nice? Use the p-value method with a 5% significance level to test the claim that the mean amount of sleep for adults is less than the recommended 7 hours. So that's a claim that we're going to test with a hypothesis test. So before we go into the process, they want you to look at the requirements. And it is possible you'll have a homework problem where they do this, they give you data, they say that you want to see if you can do a test, but that actually somehow in the problem you're supposed to indicate, oh, well, actually we haven't met the requirements, so we can't do the test. And so one of two things needs to be true to meet the requirements. You need to have a sample size over than 30, or you have to have some belief that the sample was drawn from a normally distributed population. So why would I have that belief? Well, they could just say that in the problem. They could say, assume, sleep values are normally distributed in the population. But it didn't say that here. Then they could also just give you data values where there's more than 30, but they didn't. They only gave us 12. So let's look at what they have to say about the conditions in this case. The sample is a simple random sample, so that did say that in the problem. But then it says the second requirement is the population is normally distributed or N is greater than 30. The sample size is 12, which does not exceed 30, so we must determine whether the sample data appear to be from a normally distributed population. So as I mentioned when I scrawled that out on the earlier slide, you can check that by making a quantile plot, a QQ plot. So it says the accompanying histogram and normal quantile plot, along with the apparent absence of outliers, indicate that the sample appears to be from a population with a distribution that is approximately normal. So because of that, both requirements are satisfied. Requirement 1, simple random sample, and requirement 2, that you meet at least one of the conditions, and we did because we believe the population is normally distributed based on the histogram and QQ plot we got from our sample. Okay. So as usual, we then want to set up the hypothesis test. And you set up the hypothesis test just based on the claim, not using anything about your sample. Typically, people set up their hypothesis test before they even collect their sample data. So the claim is that the mean amount of adult sleep is less than 7 hours. And so that becomes mu is less than 7. Like in the sample that I was giving where I said mu is less than 6 feet. In this case, mu is less than 7 hours. So then based on that and thinking about, well, the alternative to that would be greater than or equal to 7, we then create the null and alternative hypotheses. And the null hypothesis always involves equality, where you state that the mu value is equal to the specified number, 7 hours in this case. And then the alternative hypothesis will be either less than, greater than, or not equal to. If our claim is less than or greater than, then the alternative hypothesis will be our claim. As in this case, the alternative hypothesis and the original claim is that mu is less than 7 hours. If our original claim had been that mu is equal to 7 hours, then the null hypothesis would still be equal to 7, and it would be our claim. And then the alternative would simply be that mu is not equal to 7. And you'll see examples of both of those kinds in the assignment problems. All right, so in this case, we have set our null and alternative hypothesis. And they did tell us a sigma level, I think, of 5%. Yeah. So then we need to know our, I meant sigma level, our alpha level, our significance level of 5%. And so then what we would do is get the p-value. And if the p is less than alpha, reject the null hypothesis. If the p is low, the null must go. Now, it says because the claim is made about the population mean, the sample statistic most relevant to this test is the sample mean, and we use the t distribution. So you do need to select the correct distribution. And again, in this case, it's a t distribution because the standard deviation of the population is not known or not given. So then they're showing how to do it with the formula, but we would just enter our sample material, in this case, the values themselves, the data, into StatCrunch, and we would get this t statistics, t stat. The t stat is what they refer to as the test statistic. And that's provided by StatCrunch. But as they provide the test statistic, the t-stat, they'll also give us a p-value, which we can compare to alpha. So they're showing different types of technology and saying if you're going to use technology, it should give you a p-value. It would also give us the test statistic as well. So here's our box that we'll expect to get from StatCrunch. And so there's the t-stat and there's the p-value. So equipped with those things, we can make a solution. Because the p-value turned out to be a little less than 39%, because that's greater than the significance, the alpha value of 5%, we fail to reject the null hypothesis. If the p is low, the null must go. If the p is not low enough, then we fail to reject the null. There is insufficient evidence to support the alternative claim and to reject the null claim. So the interpretation, because we failed to reject the null hypothesis, we conclude that there is not sufficient evidence to support the claim that the mean amount of sleep is less than 7 hours. So I think initially you'll just try to get through the problems and understand the process of a hypothesis test. And I think the key to really understanding how it works and why it works is to understand what the p-value is. So I would recommend that you as a student trying to learn and understand this material, focus on the concept of the p-value if you can, and try to understand what that means. Try to make statements as to what the p-value tells us. So let me try to do one for you here. P-value of 0.3887 for this example. What does that mean? So again, we had null hypothesis, mu is 7. Alternative hypothesis, mu is less than 7. We had an alpha equal to 5%. And then we had some sample data of 12 different folks and how long they slept. So when technology takes all that data and our alpha value and it takes our null and alternative hypothesis and it says you have a p-value of 0.3887. What the heck does that mean? What does that mean? So the thing to remember is that this is based on assuming that the null hypothesis is true. The null hypothesis is assumed when you make the t distribution. You're assuming that that is the population mean, that the population mean is 7. You're assuming that that's true. So what the p-value tells you is that if that is true, and you make that assumption, then the p-value is the probability that your sample would come out the way it did, assuming that mu is equal to 7, assuming that the average amount of sleep adults get is 7 hours. So this basically says, meaning of the p-value if the mean sleep time is 7 hours, then there is a 0.3887 chance, or 39% chance that our sample would come out the way it did. By random chance, by random selection. So the idea here is that when we get a p-value, make that go away. When we get a p-value, it's telling us the probability that our sample would come out the way it did if the null hypothesis were true. So in this case, there's almost a 40% chance, if the average amount of sleep that people get is 7 hours, that you would get the sample the way you did, just by randomly picking people. And so since that's not unlikely at all that that could occur by random chance, well, then obviously your sample is not going to say, well, you should see this sample as a reason to believe that people get less than 7 hours of sleep, because it's very easily a sample that you could get if people got 7 hours of sleep. Now, if the p-value is much lower and it becomes extremely unlikely to get a sample like this, assuming that the average sleep is 7 hours, well, then that is evidence to cause you to reject the idea that the average sleep is 7 hours because the people in your sample had so much less than that, that you say, wow, well, this sample is very hard to believe that I would get that randomly if people really slept 7 hours on average. So I think this is sufficient evidence to reject that and support the claim that people actually get less than 7 hours. So a low p-value would allow us to draw that conclusion, but the p-value we got was so high and doesn't really show that this is a rare occurrence at all when people are sleeping 7 hours, then it's not evidence against the fact that people sleep an average of 7 hours. And so we fail to reject the claim that on average people sleep 7 hours. And this is not sufficient evidence to support the claim that people actually sleep less than 7 hours on average. Because it's not, it's very easily you could get this sample when people did sleep 7 hours on average. All right, so I think that's my last best effort to explain the p-value. I have tried to do that a few times now, and hopefully it's something you're able to start wrapping your mind around. And I would recommend students try, when they see a p-value, to realize what that means, to interpret that value and what it says about the statistics in the situation. All right, so let's see here. I think so then p-value without technology, I think I'll just stop the slides there. They're going to spend several slides now talking about without technology. Then toward the end, they say, if you do happen to know the standard deviation of a population, then you use a Z distribution instead of a T distribution. And we can just do that if we see that in the problem. So I'd rather take our remaining time and try to look at some homework problems. Okay, so I'm now looking at a problem from our homework for this week, homework number 11 on sections 8.3 and 8.4, and this is from 8.3. This is problem number 5 out of 39. So it says, use technology to find the p-value for the hypothesis test described below. So what's described is the claim is that for 12 a.m. body temperatures, the mean mu is less than 98.6 degrees Fahrenheit. The sample size is n equals 8, and the test statistic is t equals negative 1.027. And they want us to find the p-value. Anybody have an idea?
So they don't give us any other information other than that. So they don't mention if it's a normally distributed thing or if there's random samples. So are we just supposed to work under the assumption that it's normally distributed and random samples?
No, that's a very good question. What's challenging about this problem is they don't really seem to tell you anything. So we have to kind of focus. So what is the goal of this problem? The goal actually is to just use technology to find a p-value. So the requirements about having a normally distributed population and sample size and things like that, those are in order to draw conclusions and use a t distribution to help us do that. To justify that those conclusions and that process and the values we would get are correct for the overall arching population. But since they're not asking us to do any of those things, all they want is the technical side of using technology to get a p-value. And for that reason, we can just do that regardless of whether the results of a t distribution make sense for the population or not, because we're not asked to draw any results. We're not asked to draw any conclusions. We're not asked to make any inferences or support a claim one way or another. We're just asked to find a p-value. So this problem is very narrow in what it's asking from you, and it's very specific. And for that reason, we don't have to worry about those extra things. So that's a great question, and it's a good point to discuss. So do we have a way to come up with the p-value with the information given?
In StatCrunch, we use the statistics area and we go to, oh man, I forget, is it proportion stats? We used that before, but I forget if that's the one we use now.
Well, so let's have a little discussion about that. That's a good place to begin. Proportion stats is when you are investigating a proportion parameter of a population. Like what proportion of the population is Democrat or something like that. What kind of a parameter are we investigating for this problem?
They give us the t-stat to work with.
That's the distribution, right? And so t-stat is, and also it states right in the problem, the claim is about the mean. So when the claim is about the mean, you're going to use one of these two. And in this case, since they're telling us it's a test statistic, we would say, well, that means we're going to use t-stats if we're going to use a t-stats calculator. If we're going to do anything, what's involved here is a t-distribution. Does that make sense?
Yes.
Okay, so this is definitely a t-distribution. So what do I do? Do I click on t-stats? What do you think?
Yes.
T-stats, one sample. Do we have data? Do we have a summary? What are we thinking?
Is this just with summary? Because they don't give us more specific.
They certainly didn't give us the mean, the temperature values from the 8 people in the sample, right? They just summarized and said, well, what did they give? Did they give us what the sample mean was? So if I go to summary, they're going to want to know what's the sample mean and the sample standard deviation. We know the sample size, but do we know the sample mean and the sample standard deviation?
No, we do not.
We do not. So we cannot use this tool. Like I said, the challenge for this problem is that they give you so little. They don't even tell you what the sample mean was. They don't give you the sample data. They don't really do any of those things. So how are we going to get a p-value? Number 5, stumped us already. Can anybody ask a question to help or offer up suggestions? Or have we already stumped the class beyond repair?
Well, wait, so you said we don't have a standard deviation, right?
We don't have any information about the sample. We certainly don't have standard deviation of the whole population, which is why it's probably a t-distribution. And we know it's a t-distribution because they do give us the test statistic, which is t. But we don't even know the standard deviation of the sample. When we just pulled up the t-stat hypothesis test tool, it wanted all this information about the sample, either the data itself, which they certainly didn't give us, or at least a summary. And in the summary, it wants sample mean, sample standard deviation. They didn't give us either of those things. So we can't use that tool to get the p-value. We do often use that tool to get the p-value for a sample. So
Can we use,
yeah, go ahead.
can we use the Z summary thing?
Like the z-stats?
Yeah, because I thought maybe you said at one point that that could be used when we didn't have the sample standard deviation.
No, that would be, I was saying we use that if we did have the population standard deviation, not the sample.
Okay.
And that's if we do have it. If we don't have the population standard deviation, we use a t-distribution. And they are telling us it's a t-distribution. So it does feel a little funny to pull up a z tool when they're telling us a t-distribution value. And notice the z tool also wants the sample mean and sample standard deviation. Now we don't have those things. So neither of those tools will work. God darn it. Goddamn math. Make life so hard. All right, so what do we normally do with that tool? When I pull up that tool and I plug in that information about the sample, it normally provides us with 2 things, as I was just circling on the slides. It provides us with the t statistic and the p-value. Normally that tool provides both of those things to us from the sample. Remember, the test statistic is the statistic from the sample. And then they also give us the related p-value. So in this case, they didn't give us any information about the sample itself, but they are already telling us the test statistic. So they're basically telling us what the distribution score is. That's why they didn't give us the information from the sample, because they already gave us the result over here. So what's going on here is that we're using a t-distribution. And we're testing a claim that the mean is less than 98.6. So that means on our distribution, we would set the mean to be equal to 98.6 because that's the null hypothesis of that claim. And then to see what the p-value is for our sample, we would find out where on that distribution the sample value comes out to be. But they're telling us the t-score there. They're telling us that the distribution value here would be t is equal to negative 1.027. That means half the work was already done for us. That's why those tools don't apply. So the p-value we want for that test statistic would be the area here. Actually, I'm on the wrong side. I'm dyslexic. I always do that. Let me back that up a little bit because it's a less than, it's a left-tailed test, and this is a negative t-value, so I'm supposed to be over here. So the p-value that they're asking for is the area under the curve over here to the left of that test statistic. Erase some of that. So that's what they're asking for. Oh, that looks terrible. But I'm going to leave it. So if I were to simply ask you, given that t-score, what's the area to the left of that t-score for a left-tailed test, what technology tool would we use to calculate the area to the left of that t-score? Anybody know? What if it was a z-score? I think in chapter 5, we looked at the idea of just given a z-score, being able to find the area to the right or to the left of that score. How did we do that? Anybody remember?
That was just with the normal distribution. Let me see what it's called. The calculator for normal distributions, right?
Exactly. And notice that right below the calculator for the normal distribution is a calculator for t-distribution. Can you guys see that on the screen there?
Yeah.
All right. So if I pull that up, then I get this same picture. And I know the sample size is 8 and the degrees of freedom is 1 less than that. So I enter in degrees of freedom is 7. And I want the probability of getting a score less than or equal to negative 1.027. And that probability is the p-value of that t statistic. And so that's what they're asking for. Use technology to find the p-value for the hypothesis test described. And in the hypothesis test described, they got a test statistic with this value. And so the p-value corresponding to that t test statistic is basically 17%. So I would put that in and I'd be done. That's the whole problem. Number 5. Questions, comments, discussions about that? Okay, so the hard part of this problem is by reading the problem to know to go use this tool to get the answer. So imagine that this problem, we got a midterm coming up a week from Thursday. Imagine a problem like this pops up in the middle of the midterm. Problems in the midterm have been all scrambled around in order. Maybe this problem pops up right after a problem from chapter 1. How do you read this and know that that's how to get the answer? That's the hard part. Once you see how to get it, well then, oh yeah, okay, when I get to this problem, I'll just do what I saw Mr. Willett do. But how do you know to do that in general? Because you're going to have to recognize from the problem without the context of having just been shown how to do that yourself. And it may show up on the final exam as well. In which after that, we've been talking about chapters 9 and 10 and 11, and your brain's been scrambled by a bunch of other stuff. And then you go take the final and boom, this problem pops up. So I think the real recommendation I would make, the real goal would be to say, how can I look at this problem and understand what they want clearly enough to go get that calculator for the t-distribution and find out the area based on being left of this t-value. That's the p-value, is the area left of that t-value, using the correct degrees of freedom. Questions about this at all before we try to squeeze one more problem in to finish up today? This could be a very quick and easy point to get on an assignment, or it could be one where you just read it and you're like, I don't know what to do. All right, let's take a look at the next one. It's a little bit more of a normal standard problem here. All right, so it says the display provided from technology available below results from data, using data for a smartphone carrier's data speeds at airports to test the claim that they are from a population having a mean less than 4 megabits per second. So they give us a claim that was tested. We're going to obviously have to set up the null and the alternative hypothesis and pick one of these. And it says the technology results from the sampler here. So they're basically just showing some results here, and we're supposed to see how, looking at the technology results, how to answer the question, which is the position we're going to be in because StatCrunch will also give us results like this. But let's see how we could format this. All right, it says conduct the hypothesis test using these results. Use a 5% significance level, identify the null alternative hypothesis, test statistic, p-value, and state the final conclusion that addresses the original claim. So in this case, they're not giving us the actual sample values that we would put into technology to get all of the results. They're just giving us the results from the technology. All right, so since the claim that we're testing is that the mean is less than 4 megabits per second. That's the claim. So that means the null hypothesis would be that it's equal to 4, and the alternative hypothesis would be less than 4. So that is B, it looks like. So then it says, what is the test statistic? Well, normally we'd be looking that up in StatCrunch, but in this case, they're just giving it to us in this table. So they're just wanting, in this problem, that you can identify these key things that they're referring to from the technology. So what is the test statistic for this mean test? It's the mean of your sample translated into a distribution score. In this case, it gave us a t-score of negative 2.887. So rounded to 2 decimal places, that would be negative 2.89. So the test statistic is, in this case, the t-score. That's the t-score based on the mean value of 3.32. But the test statistic is the t-value, the distribution score. Okay. So then it wants us to identify the p-value, and again, that's just given there as 0.003, looks like, to 3 decimals. And then we have to draw a conclusion. So what we do is we compare the p-value to the alpha value. And if the p is low, the null must go. The alpha value is 5%. Our p-value is less than 1%, 0.3%. So the p is definitely lower than alpha. So therefore, we reject the null hypothesis. Because the p is low, the null must go. We reject it. And that means there is sufficient evidence to support the alternative claim that the sample is from a population with less than 4 megabits per second.